Deep beneath the ocean, a glowing, transparent train tunnel stretches across the seabed like a silent, artificial river of light cutting through complete darkness. The surrounding water is crushingly heavy, yet inside the tube, everything feels calm, controlled, and almost impossible. This contrast becomes even more powerful when the eye moves between the dark ocean pressure outside and the bright, futuristic tunnel interior glowing with engineered precision. A bullet train running inside a glass tube under the ocean. The idea immediately creates disbelief and forces the mind to question reality. How could something like this even survive ocean pressure that increases with every meter of depth? This is not ordinary engineering, but a futuristic vision inspired by real scientific principles, advanced materials, and experimental marine design thinking. And what you are about to see is not just construction. It is an entire ocean being reshaped through human imagination. The central mystery begins here. How would Japan build a bullet train tunnel beneath the ocean while facing unstable currents, crushing pressure, and complete darkness, even though humans already build tunnels under rivers and shallow seas? The key contradiction is clear. Oceans are unstable, high pressure, dark, and constantly moving. Yet engineering history shows that humans already cross water barriers using tunnels and bridges. This raises a deeper question. Can we go even deeper and even make it transparent? This remains a futuristic but science-based concept, not an existing real-world project built on evolving material science and design logic. Japan's engineering identity plays a central role in this vision, shaped by earthquake-resistant design, advanced bullet train systems, and large-scale coastal megastructures. Real undersea tunnels already exist globally, but they are dark and enclosed concrete systems. This concept represents evolution from dark tunnels into transparent ocean view travel designed for experience rather than only transport. The entire idea depends on combining concrete engineering with futuristic materials and marine technology, following strict realism rules like circular pressure-resistant structures, titanium and steel frameworks, and multi-layer glass systems. Now, the question becomes simple and powerful. Where do you even begin building something like this? The entire project begins far below the surface where human eyes cannot reach. Survey ships move slowly across the ocean while advanced sonar systems scan the seabed in precise layers of sound waves. These signals bounce back from the ocean floor and create detailed digital maps that reveal hidden slopes, rocky formations, and unstable sediment zones. At the same time, remotely operated underwater vehicles descend into the deep water, exploring areas that satellites and surface tools cannot understand. They capture real-time visuals, measure depth variations, and study how the ocean floor behaves under constant pressure. Drilling rigs are then deployed to extract samples from different layers of soil and rock, allowing engineers to test strength, density, and stability under simulated stress conditions. Sensor networks are placed across strategic points to track ocean currents, underwater vibration, and pressure fluctuations that change with depth and time. All of this data is collected and processed by engineering teams who begin identifying the safest possible tunnel route beneath the seabed. As this happens, something extraordinary begins to form. Even though nothing physical exists yet, a digital representation of the tunnel starts appearing on computer models. This invisible pathway slowly becomes the foundation of everything that will follow, marking the first moment where imagination begins turning into structured engineering reality. Once the seabed route is defined, construction shifts toward the coastline, where the physical work begins. Large construction bases are established near the shoreline, transforming empty coastal areas into highly organized engineering zones. Temporary access roads are built to transport heavy machinery. Cranes are positioned for deep excavation work, and vast storage areas are created for steel, concrete, and mechanical equipment. Power stations are installed to supply uninterrupted energy, while control hubs are set up to monitor every stage of the operation in real time. From these coastal bases, approach tunnels begin excavation inward from land toward the ocean. These tunnels are not futuristic yet. They are strong, conventional underground structures reinforced with thick concrete lining and dense steel reinforcement systems designed to withstand pressure, vibration, and moisture. Inside these tunnels, engineers install drainage systems to manage water leakage, ventilation systems to control airflow, and emergency systems that ensure safety during every stage of construction. These passages eventually form the essential connection between land infrastructure and the future underwater structure. This entire phase represents the most realistic part of the project because it follows existing engineering practices that are already used in modern metro and railway tunnel construction around the world. Far from the seabed, in massive coastal fabrication facilities, the most futuristic part of the project begins. Here, engineers construct large cylindrical tunnel segments that will eventually form the transparent underwater corridor. The design is based on a critical engineering principle. Circular structures distribute ocean pressure evenly across their surface, reducing stress points and increasing stability under extreme underwater conditions. Each module is built using a combination of advanced materials, starting with titanium rings that form the structural skeleton. Steel reinforcement ribs are added to strengthen the frame, followed by multi-layer curved glass panels that create the transparent viewing surface. Specialized polymer sealing systems are integrated between every connection point to ensure complete waterproofing. The manufacturing process is extremely precise. Titanium rings are machined to exact specifications, inspected for microscopic flaws, and then assembled into perfect circular frames. Curved glass panels are carefully lifted using suction-based robotic systems and inserted into the ring structure one by one. As each panel is placed, seals are compressed and reinforced using anti-leak gel to eliminate any possibility of water intrusion. End flanges are attached to both sides of the module, allowing future segments to connect seamlessly during underwater assembly. Before leaving the factory, each module enters a critical stage where it must survive deep sea pressure simulation testing. Only after passing this requirement can it be approved for transport and installation in the ocean. Every completed module is placed inside a specialized testing cradle designed to replicate deep ocean conditions. Once secured, powerful hydraulic systems gradually apply simulated water pressure, equivalent to thousands of meters beneath the sea surface. Engineers monitor the structure carefully as sensors embedded throughout the module begin collecting real-time data. They check for even the smallest signs of leakage, material deformation, stress concentration, seal weakness, and unexpected movement at connection points. High-resolution monitoring systems track how glass layers respond under pressure, while structural sensors measure titanium frame stability under continuous load. Any irregularity triggers immediate analysis and adjustment before approval is granted. The goal is absolute certainty that each module can survive the extreme environment of the ocean floor without failure. Only those that pass every condition are certified for deployment. This stage is crucial because it ensures that once the modules are placed underwater, they will behave as a single continuous structure rather than independent fragile segments. After testing and certification, the project moves into its most dangerous and visually dramatic phase. Offshore installation begins as floating cranes and heavy barges position themselves directly above the planned seabed route. The first transparent module is slowly lifted and lowered into the deep blue water, guided by cables and robotic stabilizers. As it descends, strong underwater currents begin to create alignment challenges that make precise positioning extremely difficult. Engineers must ensure that every millimeter matches the pre-installed seabed anchors because even the smallest misalignment could compromise the entire seal system. The operation requires extreme precision, as pressure increases rapidly with depth and visibility decreases. Underwater robotic arms equipped with sensors and lights assist in guiding the module into place, while control teams monitor every movement from the surface. As the structure approaches the seabed, tension rises dramatically because the success of the entire tunnel depends on this single moment of accurate alignment. One incorrect adjustment, one unstable current, or one failed seal could collapse the entire system before it even begins to function. As the installation continues deep beneath the ocean, something extraordinary finally begins to take shape. Each cylindrical module is carefully lowered and connected one by one, forming a continuous chain across the seabed. Engineers guide every alignment with extreme precision as massive waterproof sealing rings compress under immense underwater pressure. These seals lock together like interlocking shields, creating a unified structure that prevents even the smallest trace of seawater from entering. With every successful connection, the transparent tunnel extends further, transforming from isolated segments into a single, flowing corridor of engineered glass and titanium. Slowly, the vision becomes reality as the seabed is crossed by a luminous structure never seen before. For the first time, the final connection is completed, and the tunnel stands as one uninterrupted passage beneath the ocean floor. The visual impact is breathtaking, a glowing tube stretching across the darkness like a futuristic highway carved through the deep sea. In this moment, the emotional peak arrives. A structure designed to hold back the entire ocean now exists not as imagination, but as a fully formed engineered reality suspended in the silent depths. Once the physical structure is complete, attention shifts toward system integration, where every internal mechanism is activated and tested together as a unified network. At the transition zones between land tunnels and underwater sections, massive flood protection doors are installed to instantly seal off sections in case of emergency pressure changes. Along the tunnel, advanced drainage and high-capacity pump systems are activated to remove any unwanted moisture or condensation buildup. Ventilation channels are carefully calibrated to maintain stable air quality and pressure conditions throughout the entire route. Beneath the rail line, vibration isolation systems are installed to ensure smooth train movement even under oceanic stress conditions. Power rails and high-speed signal systems are connected to provide continuous energy flow and real-time communication across the entire tunnel network. Throughout the structure, artificial intelligence-based monitoring sensors constantly scan for leaks, stress variations, and structural anomalies. Before any human passengers are allowed, a strict testing sequence begins. First, an unmanned inspection vehicle travels through the tunnel, recording every vibration and structural response. After that, an empty trial train is run to verify full system stability. Only when every test is passed successfully is the system considered safe. The guiding principle is clear: safety always comes before spectacle. At this stage, the tunnel becomes more than an engineering project. It represents a deeper shift in how humanity imagines transportation itself. This is not just about moving from point A to point B anymore. Instead, it reflects a future where the journey becomes as meaningful as the destination. The transparent underwater corridor transforms travel into an immersive experience where passengers are not separated from the environment but surrounded by it. This vision symbolizes the ongoing tension between human ambition and natural limits, where engineering continuously pushes against the power of the ocean and its overwhelming forces. It also reflects the balance between technological progress and environmental challenge, showing how innovation grows when confronted with extreme conditions. Even if this structure does not fully exist in the present world, it still represents a clear direction of future development in transportation and infrastructure. The core message becomes powerful and simple. What humanity is able to imagine today often becomes the foundation of tomorrow's real-world engineering achievements. In the final moments, the vision comes alive in cinematic detail. Passengers slowly enter the glowing underwater station and step into the transparent tunnel for the first time. Outside the curved glass walls, deep ocean life drifts silently as small fish move through the blue darkness surrounding the structure. The bullet train begins its journey, gliding smoothly through the ocean as light reflects across titanium frames and glass surfaces. The contrast between human technology and natural ocean depth creates a surreal and unforgettable experience. The closing thought leaves a lasting impression. The ocean was never a barrier. It was simply a challenge waiting for engineering to solve. As the journey fades, viewers are invited to continue exploring more futuristic megaprojects in the next video. They are encouraged to like, subscribe, and share their own ideas for future engineering concepts in the comments. And finally, the story ends with a powerful curiosity hook. But the real question is, what will we build beneath the ocean next?